All right, I have a little demonstration for you that is built into Desmos, which you can access directly if you would like to play along with it yourself at your leisure. But this is a way to look at deltas and epsilons. So remember, for the precise definition of a limit, for a limit to exist, we have to be able to find a delta for any epsilon greater than 0, such that if we are within delta units away from A, as x approaches A, the function values are within epsilon distance away from L, the limit. And so in this case, we have a graph set up. The function we're looking at is f of x equals x squared. And there's a slider that I can control to determine what epsilon is going to be and what delta is going to be. And there's a little smiley face / frown that smiles if our delta is small enough such that the function values are within an epsilon. So let me reset everything and show you what I mean. So right now, epsilon is set at 0.8, which means this vertical bit has a range that goes above and below 1 by a distance of 0.8. And so this vertical bit is basically looking at where our function values are within 0.8 units from 1, which is meant to be the limit of x squared as x approaches 1, which of course we can easily figure out by the direct substitution property. But we're going to dive deeper with these epsilons and deltas. So here, epsilon is set at 0.8, and right now delta is 1. The neighborhood we're looking at for x values is 1 unit away, either to the left or to the right of 1. And unfortunately, the part of the graph that gets colored in has y values that are way too big. You can see the y values are going all the way up to 4 there. And so we need a smaller delta. Basically, we need to decrease the interval that we're looking at the x-axis to start getting the y values in the right range. Now, if I get to about here, if you're looking at the left side of the interval, right now we've got y values that are too low, and at about here, we start to get y values that aren't too low on the left. But on the right, the y values are still too large, so we need an even smaller delta. You can see we're looking at a closer and closer neighborhood, and eventually we get to a point where the smiley face is smiling. I can't remember his name. I believe he does have a name. It's Jarvis or something like that. But eventually, if we look at our x values close enough to 1, where the distance between our x values and 1 is less than delta, in this case, my delta is 0.33, that guarantees that the y values are less than 0.8 away from 1. But here's the thing, we have to be able to find a delta for any epsilon greater than 0. So right now it's 0.8. I'm going to take it down to 0.7. So now we are a little bit smaller with our epsilon. You can see Jarvis is frowning because unfortunately the delta that we've picked, if you look at some of the y values on the right-hand side, they're just a little bit above the top of that vertical range that we have with our epsilon. So our delta is too big, but we can make delta smaller, and then eventually Jarvis is smiling because we've now picked a small enough delta. But here's the thing, we have to be able to do this for any epsilon. So if I bring epsilon down to 0.4 or so, that delta that we picked is too big here. So we need to be able to pick a smaller delta. And if we do, eventually, and I'm going to zoom in, so we're not going to see Jarvis's face anymore, unfortunately. But you can see here that I've picked a small enough delta so that all of the function values in this domain governed by delta end up giving us function values in the range governed by epsilon. But then again, if epsilon gets smaller, that delta's too big, and we have to pick a delta that's even smaller. And what this means is that effectively, we need to be able to do this no matter what size epsilon is. So if epsilon gets even smaller, we need to be able to pick a delta that's small enough. And then if we zoom in even more and we pick an epsilon that's even smaller, that's a little bit too small. Not mathematically, but just the way that this is set up, I can only make delta a certain size, and eventually it shrinks down to 0. So we can make it smaller, and then theoretically, we should be able to zoom in, and if epsilon is getting smaller and smaller, and I can't, with this demonstration, make it any smaller, unfortunately, because the computer's only built for it to get so small, but as our range gets smaller, we need to be able to find a domain that has a small enough width that we're still in that range. And it should be true for any epsilon. So it should be true for 0.01, and then 0.001, and then 0.0001, and 0.0001. Basically, we can't have those situations that we had before where either there was a gap and there was a certain point where we stopped getting closer and closer to L, or where we have weird oscillations and the oscillations are so big that we're never going to get a delta small enough that we're not oscillating outside of that epsilon. That is kind of the best I can do right now with this particular demonstration to give you an idea of what's going on with the deltas and epsilons. I do have an example video that shows algebraically how we can figure out what delta is in terms of epsilon, so that no matter what epsilon is, we can pick the right delta. I encourage you to watch that video, but this is kind of the best demonstration I can give with this Desmos demonstration. And zooming out, you can see exactly how tiny these are compared to what we were looking at first. So no matter how small the epsilon is, we need to be able to find a delta that works, or the limit doesn't exist.